All right, let's do this. Hello everyone, it's January 31st. We haven't hit February yet. Oh, my leg is sore. But we have a max out session. I'm actually pretty excited. Alright, so finally we hit an easy one. So what we're gonna do is we are going to read through a couple of things. So one at a time. I'll read through this one first. This is using coloring. Not sure what that means, but I'll read through this one first. Okay, let's solve it first. Array considered special if every pair of its adjacent elements contains two numbers with different parity. You are given an array integers, return true if nums are special, otherwise false. Okay, we just need to check the parity to see if it's alternating, and then that shall be it. It will be interesting if there's like another way of doing this. I don't think so. I think you just go down and then like what you need to check we start from the second one, right? Then we check if the current and the previous is the same. Basically, that's if it's the same, then you return false. If it's different, then you just keep going. So essentially, I think that we'll have to make directory, and this has to be 2, and this is 2. Okay. So essentially, what we're gonna do is this. For int I equal to 1, I smaller than nums dot size, I plus plus. If nums I mod 2 is equal to nums I minus 1, that's a misspelling, I minus 1 mod 2, that means the parity is the same, then we will return false. Otherwise, we'll return true at the end. That shall do. This is 3151. All right, we'll run through these examples. Solid. Okay, so we're done with this, which is good, but let's move on to what is most important. So this is yesterday's problem. We use union find and BFS. No, that's a different problem. I think this is from the day before yesterday, which was find nodes into maximum number of groups. So you, you essentially BFS this thing. And the way I was doing is your BFS, and if at each level, because you can only group the nodes that's on the same level into a single group. You cannot group it with people above you. You cannot group with people with nodes below you. You can only group with the same level. And if there is a link between the nodes on the same level, that's impossible. So that's essentially what this is. Otherwise, you just keep going and you return the final level. And we brute forced this by going through every single one, because we start a little bit more complicated than this, I think. Oh, because it can also be disconnected, right? So as we go through this, yeah, yes. So basically, within each component, within each connected component, you will have to decide what its um, you have to decide its what's component, like if we have as a component index, right? Which means for this node, which component belongs to. If it's smaller than 0, which means we haven't found any component for it yet. So we'll go through the BFS on this, and this one will give us the maximum levels starting from this, and then we push it into the components, right? We have a components array, and we basically also have its um, index as well. Where do we update the index? Oh, index is here. Index and index map, right? So essentially, we will do the index map here, and then we'll do index map for every single node. So basically, this one, after we're done, all the index for the component is mapped to the nodes. So this is like that, and because we go through every single node, so you will either do it in fresh or you have already had it. So you basically get the component index and you try to find the maximum number of levels, and you assign back to this, and then you have to go through this one more time because each component can produce a level. But if one of them is smaller than 0, which means one of them is not possible, then you need to return -1. Otherwise, you just add them together. Okay, so we went through this. Now let's read this solution approach 1. All right, let's just go through the start. So we're given this represented by the 2D array. Each node exactly one group. Sometimes this can split. It's not possible. Invalid because they have a link in between. Invalid because we have a cycle. So these two should be by 1. A key observation is that if it's possible to divide the nodes into x groups, we can also divide them into x minus 1 groups. Intuitively, this works because the nodes in the first and third group can be directly connected, but they must all connect to the nodes in the second group. By combining group 1 and 3, we can get. So essentially, by combining group 1 and 3, yeah, because these can be connected together. The reason being they do not have a connection. So, okay, they have this observation. I never used it. So to check if a valid split is possible, we just need to see if the graph can be split into 2 groups. In other words, whether it is a bipartite. Then what? A graph is bipartite when we can divide its nodes into 2 distinct sets where all edges connect vertices from one set to the vertices in the other. No edges exist between vertices within the same set. Yes. Another key detail to consider is that the given graph is not always connected. In this case, we calculate the largest number of groups for each connected part and then take the sum of these numbers. Yes. The sum of the problem boils down to these. Check if the graph is bipartite to see if a valid split exists. For each connected part of the graph, find the largest number of groups we can divide the nodes into and return their sum. So we do graph coloring and the longest, shortest path. Yes, longest, shortest path is just the number of levels. So to solve the first part of the problem, note that once we assign a single node to one of the two groups, the rest of the assignments are automatically determined, because once you assign one node is red, everything it connects to becomes green, and everything they connect to become red, right? So if I go red, green, red, green, red, green, right? Eventually, if a node connects to another node who has the same color as itself, then that means it's not possible. So to check if a bipartite, we color the nodes using two colors, ensuring that any two connected nodes have different colors. If this coloring fails, the graph is not bipartite, and we can immediately return the -1. Yes, so red, green, red, this is green, so this shall be a red. But at the same time, this shall also be a green, and this, yeah, it cannot be colored either. Oh, that's where the coloring comes. Okay, that makes sense. If the graph is bipartite, we can calculate the max number of groups we can divide the nodes into for each connected component. In order to achieve the largest number of groups, we spread the nodes as far apart as possible. This means that instead of simply assigning a neighbor node to the same group as the one it was previously associated with, we always try to assign it to a new group. An important observation here is that the maximum number of groups is a component is determined by the longest, shortest path between any pair of nodes in that component. This is similar to finding the height of the component if it was structured as a tree with different nodes as potential roots. The longest, shortest path essentially tells us how many layers or groups can be created based on the distance between the nodes. That's essentially what we are doing, the BFS. We repeat this for all connected components of the graph and sum up. All right, let's go to the code. Maybe Python will be easier for you to pause, because lordy, this one is long. All right, so we get this is, did we do the same thing? Yes, we do the same thing, right? We use this to get a graph, and this is the colors. And then we call is bipartite, which will return true or false. So we start coloring from uncolored nodes. If is not equal to 1, which means being colored, we can continue. If it's not being colored, we color 0, and then this, I think, probably just a BFS. Okay, yeah, bipartite. Yep, it's just a BFS, right? So we go to the neighbors. If the neighbors, yes, if your neighbor color and you are the same, it's bad. If the neighbor is already colored, you can skip it. If the neighbor has not been colored, then you can use exclusive OR for this, right? If it's a 0, become 1, if 1 becomes 0. And of course, this one also work. And then you check this, and then, okay, yeah, bipartite is easy to understand. So we run this to the side. Okay. And then we'll calculate the lowest, shortest path. Let's see how they do that. So this is the distance. So basically, starting from each node, what is the distance, right? Is that what it is? Yeah, so for this node, we get this distance. But how do you know which nodes belong to the same group? Longest, shortest distance. Right, let's see what this function does. I'm pretty sure this one shall be BFS. Yes, this is a BFS. Oh my god, what happened? Why is it so slow? Unreadable. There we go. Okay, the longest shortest path. We have adjacency list. We have the source node, and we have the total number of nodes. So initialize a queue, visit it, and then because we already decided that this is a bipartite, right? So this means when we run this, we don't have to use a set. We can just use a queue. So layer by layer, get the size, get through them, and then we'll pop these for each one. We add to the next distance plus plus, and then return the distance. Okay, so that's good, right? So this is basically calculate the height of the tree based on each node, starting from each node. Where were we? We are here, so we get a distance. So now we know from each node what is the distance. The next question is, how do you know who they belong to? Dear me, you do another one. What is that? Get number of groups for component. So we go through each one, and we have a new visited. If it's this, then we do this. So number of groups. So we have distance. We have adjacency list, so I have the node. So essentially what I think this is doing is we go either BFS or DFS one more time, and we'll just return the distance. Because distance is the number of groups. Let's see if that is what we think. Yeah, so max number of groups. So max number of groups starting from the current node, right? And then we visit it, and then we go through our neighbors. And then we can go to, so you get the distance, get the maximum distance from them. So basically you DFS this whole tree, and at each point you will try to return the maximum value, the maximum of the number of groups. Basically the maximum distance starting from each position, and eventually get a max. So this will give you the max of all the components, right? Of the components. And we are here. So you get a max component, so you plus and then eventually. Okay. Yep. So I would say the way I would do it to improve upon this will be use the coloring method to decide if it's possible. Right? If splitting is possible, and then after that we'll know it is possible. So we can run this BFS without using any set, just a regular BFS, right? Just a regular BFS, and we use the same idea of recording which group it belongs to. I believe this is better because we only need to traverse the tree once. I think it's better than what this solution is trying to go through, but we know what this is about. The second one is essentially the same, so I don't think I'll code this, but this is a great idea by bipartite. Okay, good problem. Done. See, we're shrinking this backlog. Next, we'll try to do this. Oh, this one is Pretty tough. Spent a lot of time to get this one done. I think I have to read through what I was doing, but maybe this one should be the thing that we go first. Yeah, we should try this one first next time. Anyway, that will be it for today. I'll feed my cat and let's max out. All right.